Okay, should be recording now. Okay, so we were trying to find the pressure exerted by these particles moving in the box. And we did that by finding the change in momentum during an elastic collision with the particle and the box. Okay, so we found the change in momentum, we found the force, we took the force and divided it by the area of the impact, and we got the associated momentum. The associated pressure for the particles moving in the horizontal direction. So particles with velocity Vx. Okay, and then through integrating over all possible Vx, we arrived at the following expression for the pressure. Okay, so that was the particle density times the mass times the expected value for the velocity squared. Okay, but all of this was done for Vx. Now we could have done the same thing for Vy or Vz and obtain a similar result. Okay, in other words, we could have found the pressure P equals Nm Vy squared, or we could have done the same thing with Z. So it would be N times M Vz squared. Okay, now we don't want to work with any particular direction. So X, Y, Z, they should all be treated equivalently. So instead of working with the specific one, what we do is we work with just Vz, the square of the vector. So V squared, okay, with a bit of Pythagoras, we can write this as Vx squared expectation plus the expectation of Vy squared plus the expectation of Vz squared. Okay, so that's just a bit of Pythagoras there. Now we have an expression for each one individually in terms of Vx, Vy, Vz. If we want to write this in terms of the overall V squared, we need to have a factor of a third, okay, because there's three of them. So we can write P is equal to 1/3 N times M times V squared. Okay, so now we're writing it in terms of the overall V squared instead of any individual components. Okay, now this mv squared is looking a lot like the kinetic energy. Remember, that's half mv squared. So if we multiply by 2 and then multiply by half, we can include that factor of 1/2 that we need. So let's write this as 2/3 n times 1/2 m expectation of v squared. Now this 1/2 m, that doesn't have an effect on the expectation, because remember, that's defined in terms of an integral, and constants can be taken in or out of the integral. Okay, so in fact, this 1/2 m, we can take it inside the expectation, just as you would take it inside an integral. So this is going to be 2/3 times n times the expectation of 1/2 mv squared. Now this quantity in the angle brackets, we can call that the kinetic energy. Okay, so let's say that is going to be E. E for the kinetic energy. So we can say the average kinetic energy, or the expectation of the kinetic energy, is equal to the angle brackets 1/2 mv squared, like so. So we can write this as 2/3 times n times E. Okay, now we're almost done. Remember, n, that was the particle density. So we can write the particle density, little n, as the total number of particles, capital N, divided by the volume. Okay, so that gives us back our particle density in terms of the number of particles and the total volume. So we can substitute that, and we end up with 2/3 times n over v times E. Okay. Sorry, if we write this E, let's call that E0. So that's for a single particle, expectation, E0. So that's E0. And then let's say E, so that's E0. Let's say E is equal to N times E0. So that would be the total kinetic energy. So E0 is per particle. And E, this is for all the particles, so total kinetic energy. Okay, so finally, we can write this as 2/3 N times E naught. That's going to be the total E divided by V. Okay, so we see that the pressure of a system is 2/3 times the energy density. So the total energy divided by the volume, we can call that the energy density here. Okay, and I think in the next homework problem, the hand-in problems, you're going to repeat this calculation, but instead of classical particles bouncing around in a box, you're going to do it for photons or radiation in a box. And you'll see that we get a different prefactor here. Okay, that's because you're dealing with photons instead of classical particles. Okay, but for classical particles moving around in a box, the pressure is 2/3 times the energy density. Okay, any questions so far? Okay, so we've got a little definition or little theorem, sorry, and that is the equipartition theorem. So you would have done this in first year, but we're just going to go through it again. So the equipartition theorem theorem. Okay, so the equipartition theorem says that each degree of freedom sometimes abbreviated as DOF. So each degree of freedom of a system contributes an amount 1/2 kBt to the total internal energy of the system. Sorry, total, not total energy, total internal energy. Okay, so if you have one particle moving in 2 dimensions, then since it's moving in 2 dimensions unconstrained, it will have 2 degrees of freedom, and so 2 contributions of this factor. If you have a single particle moving in 3 dimensions unconstrained, then there are 3 degrees of freedom, and so 3 contributions of this factor. And that's where we get that factor 3/2 in kBt, okay, because there's those 3 dimensions there. And then, like I said, if you have n particles in 3D, then you have 3n contributions. So, example, n particles in 3D. So by 3D, we mean 3 degrees of freedom for each particle. So 3 degrees of freedom per particle. We have 3n amounts of this, because remember, it's the 1/2 kBt for each degree of freedom. If you have n particles, it's going to be 3 times n times that. So in total, we have, 3n times this 1/2 kBt. And then that gives us our 3/2 n kBt that we've been using so often for the internal energy of an ideal gas. Okay. And if you convert this from number of particles to moles, then we get our 3/2 nRT. Okay, so that's what we've been using before, but it's exactly the same. So if you want to work in number of particles, you use this one with capital N being number of particles, or you can work with this one with little n being number of moles, but it's exactly the same thing. Okay, so the first one, that's n is number of particles. Again, each with 3 degrees of freedom, or you can have little n being number of moles. But again, 3 degrees of freedom for each particle in your amounts of moles. Okay, so this is the important 3 over here for the 3 dimensions. Okay, and of course, if you have extra degrees of freedom, such as rotation, so you can rotate around the x-axis, y-axis, or z-axis, all of those extra degrees of freedom due to rotation or spinning or whatever, you add that as well. Okay, so if we have some kind of extended molecule, so 2 particles joined together, this one can now move in 3 dimensions as a single object, but we can also define a rotation axis, and it can rotate around that axis. So that is an extra degree of freedom that this has. So extended bodies like a diatomic molecule, maybe this is like n, so like, okay, well, let's not use n, that's confusing. Let's say O and O, so O2. Okay, so an oxygen molecule. So extended bodies like a diatomic molecule will have extra degrees of freedom because of the rotation. Extra degrees of freedom because they can rotate. Okay, so single particles can't really rotate because they're just point particles. However, if we have something extended, like this rigid body molecule, then of course you have that extra rotation out of the different axes. Around the different axes. Okay, and then you would have to add that as well to your total contribution. All right, any questions on the equipartition theorem? Okay, so let's apply the equipartition theorem to the work we've been doing with the pressure. So applying the equipartition theorem. Okay, gives us, okay, so remember it's 1/2 kBt for each degree of freedom. So here we have that the expectation of the kinetic energy, 1/2 mv squared, is going to be equal to 3/2 kBt. Okay, 1 for each degree of freedom. Okay, so with this, we can then write that the pressure is equal to 2/3. Okay, like we had before, times n over v, that was our particle density, times 3/2 kBt. We've just introduced that now. So this bit goes there. The 2/3 and the 3/2, they're going to cancel out. So we end up with PV is equal to NKBT. Okay, so that's in terms of the number of particles. We could also write this in terms of the number of moles. Okay, with Avogadro's constant, we can write this as nRT. And this is the equation of state, okay, that we've been using so often. Okay, so we found the equation of state from a microscopic perspective. So we considered the individual particles bouncing against the walls, and by taking averages over all of the particles and all the possible velocities, we end up with the equation of state that we've been using before. Okay, but this time from a microscopic perspective, rather than the macroscopic perspective that we covered at the beginning. Okay, so equation of state from a macroscopic perspective. Okay, and of course we also have the internal energy from this example here. Okay, so we've got the internal energy, we've got the equation of state, and you can continue, you can find the heat capacity if you want, you can find the entropy, and so on, all from a microscopic perspective. Okay, are there any questions on this so far? Okay, so everyone's all right with this. Okay, so if I just go back here, sorry, on the previous page. Here we go. This bit over here, this expectation of the velocity squared. So we never actually calculated what this expectation is. We just left it as an expectation value, or in other words, we left it as an average, and we did all our working using that. However, what we really want to do is find out what is this distribution. Okay, this probability distribution here that we used, this over here, the distribution of the velocities, what is it exactly? Okay, so we're going to try and figure out what is that probability distribution, rather than leaving things as averages, which we've done here. Okay, so question, what is the distribution of velocities? We know there must be some kind of distribution. So given a fixed amount of energy, that energy is distributed amongst the particles. Some particles might have a big velocity, some might have a little velocity, some of them a little bit in between, maybe another one with the large velocity, maybe a few more with little velocities, something like that. There's a distribution of velocities from small velocities to large velocities. And again, out of all this velocity distribution, it must be a fixed total amount of energy. Okay, but how is the velocities, or sorry, how are the velocities distributed? Okay, so what we want to do is find some kind of distribution, let's call it F, and this is going to depend on a given velocity. So if you provide me some velocity, I can tell you how likely that velocity will be. So maybe for low energy systems, small velocities are going to be more likely, okay, because there's not enough energy to go around. However, if it's a very high energy system, you are more likely to find large velocities. Okay, so that's what we're trying to work out. Now, remember what we said at the beginning of all of this. We're considering the so-called homogeneous and isotropic systems. In other words, there's no preferred direction. So particles moving along the x direction or particles moving along y or z, it doesn't really matter which direction we pick. We should get the same sort of behavior. So the distribution over the velocity vectors should be equal to some function h, so that's a new function, of just v squared. In other words, it doesn't depend on the directions, which the vector suggests. So this suggests direction dependence. Okay, we don't want any direction dependence. So if we only look at the magnitude of the velocities, then we're not talking about any specific direction. So not talking about any specific direction. So that's our first little assumption. We're going to say no direction dependence. Next, we're going to say that this velocity squared can be decomposed into the x component, y component, and z component. Again, just doing a bit of Pythagoras. So h of vx squared plus vy squared plus vz squared. But of course, if it doesn't depend on any particular component, then this can be broken up into 3 separate distributions being multiplied together. So this is some function g of vx squared, g of vy squared, g of vz squared. Okay, so again, we're not talking about any specific direction, and vx, vy, vz are taken to be independent. Okay, so each direction is independent of the others, sorry. Okay, so we have that our distribution breaks up into a product of 3 functions like this. Okay, now we're going to be doing a little change of variables just to simplify things. So v squared, we're going to call that x. Okay, vx, we're going to call a. vy, we're going to call b. And vz, we're going to call c. Okay, so it's just to make things look a little bit better. So we can rewrite this as h of x, okay, which is what we're trying to find, is equal to g of a times g of b times g of c. And we know that x, that's vx squared, squared, squared. We know that x is equal to a plus b plus c. Okay, so anyone lost with this change of variables? Okay, so what we're going to do now is take a few derivatives, and we're going to use that to figure out the shape of this h function. So what kind of function is it? So first, we're going to take the derivative with respect to a on both sides. Okay, so that's our first bit. So it's going to be d by dA of h of x is equal to d by dA of this product. Okay, so d by dA of h of x, we're going to need to use the chain rule because h depends on x and x depends on a. So we can write this as dH by dx, dx by dA, and this is equal to d by dA. That only affects the first term. So this is going to be g prime of A, g of B, g of C. And dx by dA, that's just going to be 1. So we're left with dH by dx is equal to g prime of A times g of B times g of C. Okay. Next, we're going to divide through by the following equation. So divide by h of x is equal to g of A, g of B, g of C. So our original equation, we're going to take our new equation here and divide by the original equation. So on the left-hand side, we have dH by dx times 1 over h is equal to, and then if we divide the right-hand side by this right-hand side here, we're going to get g prime of A over g of A. And notice that the g of B and the g of C, they cancel. So note g of B times g of C goes away. Okay. Now, since g was only a function of A and g prime is only a function of A, that means the right-hand side is only a function of A. Okay, so with that, we know that the left-hand side cannot be a function of B or, so the left-hand side depends on x, A, B, C, because remember x is a function of A, B, and C. So if h is a function of x, then it's also a function of A, B, and C. But the right-hand side only depends on A. So let's just write that a bit clearer here. Right-hand side depends on A. Okay, because it's g prime of A divided by g of A. Okay, so that gives us a constraint on what this right-hand side, what this left-hand side can be a function of. Okay, because we've got the right-hand side only depending on A and the left-hand side depending on X, A, B, and C. We can repeat this process by taking derivatives with respect to B and C. So for 2, we can take d by dB of h of x is equal to d by dB of g of A, g of B, g of C. Okay, and we will get a similar differential equation, but now the right-hand side will be g prime B over g of B. So in that case, the right-hand side will only depend on B. So you can do the derivatives and check, but now the right-hand side depends on B. And then you can do the same thing for C. So we can say d by dC of h of x equals d by dC of g of A, g of B, g of C. Okay, and exactly the same as before, but now we have the right-hand side depends on C. Okay, so in the first case, it only depended on A. In the second case, it only depended on B. And in the third case, it only depended on C. But notice how the left-hand side is exactly the same for all 3 cases. Okay, it's exactly the same. Therefore, equation 1 and equation 2 and equation 3 implies that this left-hand side must in fact be a constant. Okay, because that's the only way that these three equations are satisfied. Therefore, the left-hand side, so we must have that dh by dx times 1 over h of x must be equal to some constant, let's call it lambda. Okay, so that's the only way for these three equations to be satisfied. So you can check for yourself, look at all three equations and the dependency on the left and the right, and you'll see that the only way for that to be satisfied is if for the left-hand side to be a constant. Okay, so we can take this h of x over to the right-hand side, and we get dh by dx is equal to lambda times h of x. Okay, so this gives us a separable differential equation. We can solve this quite easily, and we end up with h of x is equal to a e to the lambda x. But remember, x was just v squared from the beginning. So if we substitute that back, we get h of v squared is equal to a e to the lambda v squared. Okay, so that is what our function h looks like, okay, from that beginning. So remember, we had f of v, and we said that this must be equal to h of v squared. If we're not going to put any emphasis on any particular direction, it must only depend on the magnitude. And we figured out that this h function needs to have the following form, or the following shape. So it must be equal to a e to the lambda v squared. Okay, but we still don't know what a is, and we still don't know what lambda is. However, we can figure out a little bit of information about this lambda, because we know that this has to be a probability distribution. Remember that that's what we were trying to work out, the probability distribution over the velocities. So since f is a probability distribution, we must be able to normalize it. Okay, like you normalized your wave functions in quantum mechanics, a very similar thing here. So we must be able to normalize it. In other words, the integral over all possible velocities, if we integrate this, we must end up with 1. Okay, after normalizing, we must end up with 1. So this lambda cannot be a positive number. If lambda was positive, then this expression would go to infinity when v goes to infinity, and thus it cannot be normalized. Okay, so we say it's unbounded. So we know for a fact that lambda must therefore be less than 0. So therefore, lambda must be negative. Okay, for this function to be bounded. So what we can do is we can take lambda and replace it by minus lambda. Okay, just to emphasize that this quantity is negative. Okay, so we're going to take lambda to be positive and then put the minus in front so that we get e to the minus lambda v squared, and thus making it bounded. So the lambda value to be positive, minus lambda we know is now negative. Okay, which is what we need. So we have f of v is equal to h of v squared, and that's equal to a e to the minus lambda v squared. Okay, so that's what we've got so far. Okay, so we're going to leave it at that for today. Tomorrow we're going to finish off with this distribution by finding the values of A and finding the value, the value of A and the value of lambda. So we have A and we have lambda. Once we found those two values, then we have completed finding the distribution. All right. Any questions so far?
So for our test, like what type of questions you can expect from like the section?
You'll see that in the assignment and the next hand-in problems. It will be something like that.
Similar to that though.
Yeah. So the questions in the assignment and the questions in the hand-in problems, same type of question, same kind of difficulty.
Okay. We're writing the test next week, right? Tuesday.
Next week, Tuesday. Yeah. So we will finish kinetic theory tomorrow, and then any extra time we have after that, that will be revision.
So just one more question. You know, you sent on the group the extra questions.
Yeah.
Oh, for the first one, when you sent for the PV diagram, is it it's supposed to be a straight line from A to B, or it's supposed to be curved?
No, it's a straight line. I try to make it look as straight as possible. So from A to B, that's a straight line.
Okay, thank you.
Sure. Okay, so I'll see you tomorrow where we will finish off finding this distribution, and then we'll look at some problems involving the distribution. Okay, bye everyone.